All right, everyone, good morning. Welcome back, class. Just a few seconds here, really about a minute and a half, 2 minutes, and then we'll get things going for today. Hope you guys having a good week, slept well. Hi, Eamon. Good morning. Stephanie, hello. Hello, Angel, Jerry, Cameron, Brittany, everyone. Welcome back. Mia, Leo. Kenny, Alexis, Nathan, welcome back. Good to see you guys. Sheely, Allison, Katan, Sergio, Kevin. Welcome back. Hey, Justin. Melanie, Jocelyn. Thank you, guys. Oh, 1 second, I'm just getting myself a little drink. I realized I didn't grab one. Okay. All right, great, guys. Thanks again, as usual, for being here and for making the meetings fun and interesting. So yeah, let's just continue. We have another lecture on this topic that we got started on last meeting, which is time and the metaphysics of time. So time is an interesting and a deep concept to analyze and to try and understand philosophically and scientifically. So to give us some help in getting to that more detailed understanding, we started with the work of Albert Einstein. And we looked at some of the material from his 1916 book called Relativity. In our textbook, they just labeled the title of it Time and the Relativity of Simultaneity. So what I'll start off here with is just a quick overview of the work of Einstein that we did last time, just to kind of keep us on topic. And then I'll segue into the next author in the series, who would be Theodore Cider. So, okay, first of all, Einstein starts with this hypothetical scenario. He says, suppose that there are two lightning strikes which occur at these two separate points along a railroad track. So suppose that just is the track there, that line, and we've got these two lightning strikes that happen at the two separate points on the track, A and B. He says, let's suppose that the two lightning strikes are simultaneous, and it sounds like that's an easy enough thing to just understand, but Einstein kind of forces us to give a more in-depth explanation. What does it mean? What's the definition of simultaneous? And he says it's not so easy to define the concept as it might seem, because any definition of the concept will essentially just repeat the words same time as, which doesn't add anything to the understanding. What does it mean for the two events to happen at the same time? So he insists that we be able to define a experiment or test which could be used to determine whether the two lightning strikes were simultaneous. And he says, unless we have the means and the method by which to test the question of simultaneity, then we may be using the word without any actual definition or scientific meaning. So what's the test? To determine whether they're simultaneous. He says, let's try it this way. Measure the distance between A and B. Find the midpoint between them, M. That's the point that bisects the line. Place an observer at M, who's able to see both of the points A and B in one field of vision. Now, if this person is equally far from A and equally far from B, positioned at the midpoint, and if the speed of light is always the same, then given the observation that they reach him, the two light signals, at the same moment, they would have had to travel an equal distance at the same velocity, and therefore we could interpret that they departed from their two origins at the same moment. So simultaneity then becomes defined as whenever two light signals from two separate events reach an observer at the same moment, when they're wherever they're positioned in space. But this quickly starts to show that the concept of two events being simultaneous is not absolute, but rather it's relative. To show this, we add a second observer to the same scenario. The second observer, we imagine, is positioned on this moving train, which is going from left to right with a constant velocity labeled v. Suppose that this individual on the train that's moving passes through the midpoint, which we will designate as m prime on the graph. M prime, just to distinguish it from the viewing position of the other observer who's motionless at n. So if he surpasses the midpoint m prime, at the moment that this person's doing their own observation, standing still, the second observer will not see A and B simultaneous, because given their velocity and direction of travel, they're going to be passing the midpoint and creating a shorter gap between themselves and B, and opening up a longer gap between themselves and A. So unlike the motionless observer, who stays at the midpoint, this person's a moving target going towards B away from A. So since the two light signals are traveling at the same speed, but one has farther to go to reach the person's eye, it will be B that he perceives first because he's closer to it, and A that the person perceives second. So in the order of the experience of the secondary observer, it's not simultaneous events. It's B first and then A. So is there any objective fact about whether they're simultaneous or not? No, it's just relative all the way down. So from one observer's condition, it's simultaneous, and from the other observer's condition, it's non-simultaneous. And if we wanted to add a third possible observer who is traveling in the opposite direction, with velocity v towards A away from B, then as they surpass the midpoint, falling in alignment with the other two observers for a moment, they're going to see A happen before B because of the same exact reason, just in the opposite direction of travel. So with respect to the two lightning strikes, there's no fact that can be said about what their order is. In one account, it's A first, in another it's B first, and in a third possible case, they're simultaneous, which has these very broad and deep implications, because what it does imply is that all the events of space-time are equally real and that they're not unfolding in some kind of objective linear sequence. So if you think that the present moment now is somehow distinct and special from the past and future, this is showing us that what we regard as the past and future is itself relative. And according to another possible observer's condition, those things could be seen as having already happened or yet to happen. So we thus grant reality to all the moments of space-time to overcome the problem of relativity. And after that, I talked to you guys a little bit about the additional results that have to do with the time dilation phenomena and the twins paradox. Time dilation is a concept that can be explained by means of the example of a light clock. A light clock is a system which has two mirrored surfaces and a photon beam that bounces up and down in between the plates. And if you have one observer standing motionless with a light clock, and you have another light clock above that, which is synchronized with the first one, but we accelerate it quickly to the right, then given its velocity relative to the motionless observer, it will no longer appear to take a vertical trajectory on the path of the photon beam going up and down. It will now appear as though a diagonal. And because that diagonal angle is a longer angle of approach, it will complete fewer cycles than the one that remains at rest. Once they've been reunited, we will see the difference and the discrepancy in the two time measurements. And so that shows us that time actually does move slower for fast-moving objects through space, comparatively against those objects that are at rest or don't have the same degree of velocity. And that's a weird thing, too, because you would have thought that time can't possibly pass at different rates for different observers, that it's always constant and fixed, but it can be dilated based on how fast an object is traveling. So as I was mentioning at the close of the meeting last time, if we had the technological means to accelerate a human person close to the speed of light, then they would be passing through time so much slower than people that were not accelerated at that rate, that you would see scenarios play out like are shown in science fiction. For example, the movie Interstellar, where the astronaut Matthew McConaughey comes back and his daughter is now older than him because of how fast he's been traveling around in the spaceship while she's been at rest. So anyway, then, that's just a quick recap, crash course of the material that we covered last time. I always like to start the meeting with some kind of review, brief review of the last one. But we're going to continue from here. We still have more to say today on time. And so the second author on this topic is the philosopher Theodore Cider. Now, Theodore Cider was born in 1967. He's an American philosopher, and he's still alive. I kind of know him a little, not really, but through degrees of separation. Like I have colleagues that know him and such. He goes by the name of Ted just to his friends, but I guess for his academic and publishing career, he uses his more fulsome title of Theodore. But anyway, Theodore or Ted Cider, this is a paper he wrote in 2005, and it's just called Time. Okay, so Time by Ted Cider. So his goal within the paper is that he's just going to try to introduce us to some of the basic philosophical issues and puzzles that arise when you start to think about the nature of time and investigate it in some kind of depth. He starts by noticing and telling us that time is so fundamental to our lives that we usually just take it for granted and we don't question it. Imagine that you have, imagine the experience of a fish swimming around in the ocean, right? They're surrounded by water. All they know is water. They're swimming all the time. But probably they don't take a step back and contemplate things like, well, what is water? I mean, it would have to be obviously a high cognitively functioning fish to have such thoughts. But as human beings, by analogy, we're surrounded with time. Time is the thing that we all live according to. You get up, you do your schedule, you pay attention to how much time is left in a given semester, in your life, in a set activity that you're engaged with, in a movie, etc. So time is just how we measure out all of our daily activities and coordinate things with each other. Meet me at 3. You know, we all know what statements like that mean. And so that's something that's so common to us that we kind of just don't ever stop and say, what is time though? And what is the right understanding of it? But the author says we should take that kind of step back and ask questions like these. Because the thing is, once we start to investigate time, we realize that the ordinary things that we think about it start to break down and don't make sense anymore. One of the things that he says is so puzzling about the concept of time is the way that people say that time moves. Okay, so one of the first notes I'll put here is that the author Ted Cider says that time is very puzzling. There's many reasons for this, but one that he wants to focus on for now. Time is puzzling because people say that time moves. So I would like to see if you guys have any knowledge of what are some common sayings, phrases, or expressions which give voice to the idea that time moves. There's a couple of cliche common sayings that evoke the idea of time as something moving. Does anybody have some kind of background idea of what those phrases are? Okay, good, Naaman. That's probably the most well-known and common one, the statement that time flies. Yeah, so flying is a state of motion, right? Birds, planes fly. That's something moving through space. So when you say time flies, it's like saying time moves. But time flies is not the only one, I guess. Can anybody think of another possibility aside from the classic time flies? Maybe some of these are not tip of the tongue, top of your mind, but if you rummage around in your head, I think you might be able to find a few other possible ones. Sometimes people say time is passing us by. That's another one, Janice, that I have heard. Time is passing. So to pass something, like if you pass a car on the road, or if you pass a house as you walk, it's to move past it. So that's another motion metaphor. Time is passing. Time is flying. Sometimes people say that time moves in only one direction. That's fine, Leo. I've heard that as well. Sometimes people talk about not how fast it's going, but they talk about time going slow. So whether you talk about it going fast or slow, those are both metaphors for motion. Oh, time flies when you're having fun. You know, I got to the birthday party and it seemed like it was over in a second because it was so fun. Sometimes people say, oh, well, I'm so bored. You know, I'm waiting at the DMV and it seemed like time was moving so slow. I couldn't even, like 30 minutes seemed like it took forever. So moving slow, moving fast, passing by, running out. There you go, Melanie. People sometimes say that time is running past me so fast, or, you know, time is running out. Wasting time, well, that just refers to time as a quantity, Jesus. It doesn't really talk so much about it moving, so I don't think that's the right kind of example. Use a word that has to do with moving. Out of time, again, I guess that depicts time as something that has a finite quantity and you're running out of it. But just having the kind of concept of it being quantifiable doesn't necessarily mean that it moves. You know, like you can have a big monolithic stone structure that just sits in place and say takes up a lot of stone. But anyway, like here's another case. People say time marches on. Maybe you've heard that one. Time marches on. So marching is obviously a state of motion. Sometimes people say it flows, like it's like some kind of river or something, and that's something that moves. So anyway, what these different cliche phrases express in their various different ways is that time is something that if we think about it at all, we think about it as something that's in motion. And Jerry, I don't know, a ticking, like when I think of motion, I think of things moving, like planes flying, people running, people marching. Ticking by itself doesn't necessarily evoke motion, but I guess I'll let it pass. So anyway then, the author, now returning to his main theme, points out that this is something that's puzzling. Why is it puzzling? People say that time moves, but this is very weird because motion itself refers to time to even have a definition. So that's why this doesn't actually help us. Let me write down the next point. So time is puzzling because people say that time moves, but this is puzzling because motion, like even spatial motion, is defined with respect to time. Okay, so what we have here is this. To open up the discussion, he says, let's analyze time and get into it because it's weird when you do that. And one of the things that's weird is that people say time moves. But why is this so puzzling? It's puzzling because motion itself uses time in its own definition. So, for example, let me talk to you about motion through space. Okay, what does it mean for an object to move at all? Take this marker, for example. I have a marker right now positioned at this point on the desk. And what I'm going to do is I'm just going to move it from this point over to there, sort of to the other side of the writing. Okay, so let me demonstrate. Here we go. All right, what do you know? It happened. We made the marker move. Now, with this marker moving from one point to another, what happened? Well, to accomplish the movement, for motion to happen, the marker had to be at different places at different what? Do you think you can finish that statement? For an object to move, it has to occupy different places at different what? Talk about movement. What is movement? It's something being in different places at different what? At different times. That's right, Kobe. So for something to move, it has to change its position across time. So objects move through space with respect to time. To make that even clearer, we're going to show a graph. And the graph is depicted in the book on page 458. What the graph shows is the motion of a train, let's suppose, from an origin out of Boston to a final destination in Washington, D.C. And before I show the graph, though, let me just say this. So if motion is defined in the following way, that an object is in different places at different times, then if we plug the word time into that definition, we would get a circular definition. So if objects move by being in different places at different times, then the statement that time moves would have to mean what? That time moves by being in different places at different, what are they again? Times. But there we have used the word time in the definition of the concept itself, which makes the definition circular and therefore not explanatory. If somebody asked you, you know, what is a dog? And you said to them, anything that's a dog is a dog. That would be a circular definition because you're using the word in the definition itself. So you haven't actually explained it in other terms. So if we say that time moves by being in different places at different times, we violated a principle of logic, which is that you're not supposed to define things with the word itself. Every time you look up a word in the dictionary or anywhere else, you see it defined with respect to other concepts. So saying that time moves because it's in different places at different times just takes us into a loop. and that seems to invite an infinite regress. Here, now I'll show you this graph. The graph is going to make more explicit and clear what we've just now said, that for any object to move through space, it has to be in different places at different times. So I'll clear the board and I'll draw this graph. So in the book, this graph is located on page 458. They call it Figure 1, and they title it The Movement of a Train Defined by Reference to Time. Okay, so in order to show the graph, we have to basically draw 4 horizontal lines like this. And to the left of each of the 4, we're going to draw like a time coordinate. And so what that'll show is a lowercase letter t with a subscript. So it's like little t sub 1, little t sub 2, 3, and 4. So just read this as time 1, time 2, time 3, and time 4. So these are 4 time points that go in that sequence. Now, let's, underneath these 4 lines, list the place names of 4 different cities that the train passes through on its journey from Boston to DC. So we show this. Boston, New York, then a little further south, Philadelphia, and then finally, DC, Washington, DC. And we show the same 4 underneath each of the 4 lines. Okay, so how is it that the train makes its journey? How does it move, in other words, from Boston to Washington? Well, one way to look at it is this. At the initial time, when it starts, it's in the train station in Boston. At a subsequent later time, after this, so 2 is a bigger number than 1, so this is like a later time point. Later on, the train is now in New York. And then even later than that, as it continues its journey, it's in Philadelphia. And then finally, at the 4th and final time in this graph, the train arrives to its destination in Washington, D.C. So what the graph depicts, not to worry, hey, Naomi, what the graph shows is that for this train to move, it moves by being in these different places at different times. What if I change the graph, okay, and I drew the graph like this? The train is in Boston, 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 Boston at all 4 of these time points. If that's the way the graph was shown, then let me ask you, would it have been a moving train? If it's in Boston at all 4 times, did that train move? Hey, Madeline, if you heard my question, let me know what you think is the answer. So if I had modified the graph and it was like train, 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 train above Boston in all 4, then in that case, correct, the train would not have moved. That would have been a graph of a train that stays put in the station and never leaves. So all the time, it's in the same place, right? So like right now, I'm in this chair. And if I never leave this chair again, then I'll be in the same place all the time and I won't be moving. So for me to move, I'm going to have to move by being in a different place at a different time. If you look at all the times and you see the object in the same spatial location, then that's not a moving object. So we can only define the train moving by saying that it's in the different places at the different times. But obviously, we can't analyze the motion of time itself in the same way, because if we say that time moves by being in different places at different times, wait, let me see your question here. Good answer, Sergio. Sebastian, what if it was a train the length of Boston? I don't know what you mean by that. So like the train then, can you make the question more specific? So there's still train in Boston, but also in different places. Oh, like so the train is so long that it doesn't have to drive or something? That's a weird question. I don't know. In that case, yeah, I guess what would be the point of even having the so-called train? If it's long enough to extend into the city that you want to go to, then it never would have to move. Then that would defeat the purpose of it being a train. It would just be a big slab of metal that you could walk through. I'm not sure if I understand your question. But if the train, maybe you mean this, Sebastian, like what if the train blows apart and it's in different cities at the same time? Like, so train is in Boston and we hit an explosive, and now at the same time, it's in all four places because it's scattered throughout space? I don't know. This is a question I'm having a hard time framing. But what would be the point, though? If it was the length of Boston, so what? Then it would be a long train. That's the only answer I could really give you. But do we all understand what I've said here? That in order for the train to move, clearly it has to be in these different places at different times. And again, I'll remind you, if the train was in the same city all 4 times, then that graph would not have shown a moving train. So what you are learning is that for any object to move, it has to be in different places at different times. Even the simple motion of my hand from this point to that point is because, look at the clock, it's in different places at the different seconds that are passing. So that's how it's moving. Now, what I was trying to say is that this won't work as an analysis for the motion of time itself, though, because plug time into the given definition. If objects move by being in different places at different times, then saying that time moves would be equivalent to saying that time moves by being in different places at different times. But now we've smuggled in the word time into a definition of the concept itself. So what is time moving with respect to? Some second order sort of time? Like time moves by being in different places in hypertime. But if hypertime has some kind of sequence and order, then that would have to be positioned and defined with respect to a third order sort of time, which would then again have to be defined with respect to a higher order sort of time, and this leads to an infinite regress, which would never get us out of this circular loop where we define the concept in terms of itself. So what is a different possible way to explain perhaps how it is that time moves? He says, let's try a second attempt. Maybe what we mean when we say time moves is that the present moment is moving. So perhaps this captures the sense of the statement that time moves. The present moment keeps moving around. So let's talk about the present. The present moment, in other words, now. This is the present moment, at least for the moment. But it hasn't always been. Earlier this morning, like when you guys got up, I don't know when exactly you get up, but let's suppose that some student here got up at like 8 a.m. Well, when you got up at that point, opening your eyes, that was the present moment. That was now. But now that's the past, obviously. Now, 8 a.m. on April 15th, 2021, it's gone. It's in the past. Now this is the present moment. But this present moment will also be the past in like an hour or even just a few seconds. And what's lying out ahead of you in the future right now, say noon, lunchtime, that's the future. But in about an hour and a half, that'll be the present moment. So maybe we could say that the time is moving because the present moment is sliding its position around. Like at the beginning of the day, 8 is the present moment. A couple hours later, 10:30, like this, is the present moment. Later on, noon, 3 p.m., 6 p.m., 9 p.m., and so on. So does this essentially express the idea? It seems promising. We'll make the attempt, but spoiler alert, Ted Cider says ultimately that this is not really any better of an explanation either, and it still runs into the same problems of circularity. But let's try and draw a new graph to show what he's talking about. So this graph is also shown in the book on page 459, and it's figure 2, the moving of the present moment. So as before, we're going to have these 4 horizontal lines. And these 4 coordinates here to the left. Now, in this case, what we're going to show, instead of 4 different locations underneath each line, we're going to depict 4 different times that show on the clock throughout the day. So first, noon, like 12 noon. Then 3 p.m., a little later, 6 p.m., early evening, 9 p.m., later evening. So 12, 3, 6, 9 in each of the 4 cases here. So maybe when one says the time moves, they mean that it's like this. The present moment initially at a given point in the day is noon. But then later on, subsequently, it's 3 p.m. that's the present moment. So noon doesn't stay as the present. Later on, it's 3. Later on after that, 6 p.m. becomes the present moment. And then finally, subsequently, even after that, it's 9 p.m. So can this capture the idea that time moves, that the present moment is moving? Well, it seems like it sort of makes some sense, right? But the problem is in the graph. There's still a problem with this graph. There's something on the graph here that's not defined. I wonder if you can point out or spot something on the graph that has not been given any kind of clear interpretation, but it's essential to the meaning of the graph. Anybody have a thought or guess, even if it's just a wild guess? What could it be on this graph that doesn't have a full definition or explanation? Well, okay, Leo, you say noon. Kobe, you talk about position in space. But there's no discussion of space right now. We're just talking about time moving. Although, as you probably understand, according to space-time theory, space and time are one. But not so much that, and it's also not about noon, Leo. But there's only so many things on this graph that you could possibly point out. So I think maybe you'll get it if you just keep guessing. Jerry, it's also not the present, but I mean, in the end, that is going to be an undefined concept. There you go, William. There you go, William. You've got it. I'm glad you pointed this out. So you're pointing to the time coordinates on the left, T1, T2, 3, and 4. Those are the things that are not defined. Because what are those 4 points? What do they seem to refer to? If I asked you, what are these 4 things, what would you tell me? You would tell me that they are what on the graph? What do you think T1 through 4 stands for? 4 different what? What would be your guess? I mean, T is a hint, I guess. At least T1 through 4 appear to refer to different times, like an initial time, a later time than that, and a later time than that. But how are these 4 things organized into this linear sequence 1 through 4? Like, what makes 1 prior to 2 and 2 prior to 3? These appear to be time-like coordinates, but we're trying to define the motion of time itself. And now again, it looks like we're saying that the present moment is moving by being in these different places or different positions of the clock at these different times. And so for these things to be somehow sequenced in this ordering of 1 through 4, we would have to position them in an even bigger graph, according to which they fall in this given order because they are sequenced in a broader kind of time frame that captures them. And so it leads to another infinite regress. If the present moment is moving with respect to this time designation, then these time designations have to be organized within a broader graph that has a third order sort of time that can organize them. And so it seems as if we're not getting to the non-circular analysis of time that we would have wanted. Every attempt to define how it moves leads us back to the word time itself again. So now Ted Cider has a suggestion for all of us. He says, I've got a better way than to get away from this problem, to escape from the problem of having to explain how it is that time moves, which seems to have us all tied up in knots. He says the best way to get around this is to simply have a full-on embrace of Einstein's space-time theory, because according to the space-time theory, time doesn't move. In the space-time theory, all the events of space-time equally exist, and so there is not just the present moment. There's the whole past and the whole future, and they're all equally existing at once. So on the space-time view, there's no need to explain how time moves because it doesn't move. If it doesn't move, then there's nothing to explain. So instead of thinking of time as a moving system, you should just think of it as something that together with space is a big container that just contains all the events, and all the events are equally real, including the past and future. If this is what we hold, then the present moment is no longer special or privileged. All those phrases and sayings that people have, like embrace the now, carpe diem, today's the only thing, the past is gone, the future is yet to happen, that's not true at all according to the space-time theory. On the space-time theory, the whole future already exists, and the past hasn't gone anywhere either because all the events of the past are also within space-time. This is sometimes referred to as like the block universe view, where all events and objects that ever exist in the universe are all found within the big superstructure of space-time. So your idea that this present moment is the only thing that's happening or the only thing that's real is itself an illusion. And this is a weird, heady idea, but it is a direct consequence of Einstein's physical theories, and it is the dominant consensus view within physics and science, as strange as it may be. One of the benefits that it gives us philosophically is the benefit that Ted Cider is talking about. If we embrace the space-time theory, then we no longer have to go through this messy business of trying to explain how it is that time moves, because we just give up and say it's not moving at all. All the events are out there. So there's no coming into being. There's no passing out of being. Nothing starts or stops. All the events are all just there forever. So how then can we reconceive of objects and events according to the space-time theory? William, you say this. This opens a different can of worms, though. All contingencies exist, like whether I choose to eat eggs or bread in the morning. Yes. I mean, William, definitely. According to this view, everything that you ever do is all set out, and there's no free will and there's no open future. When you look back at the past, William, and you think nothing can be done about that, I made a choice back then and I can't undo it, you understand that the past is permanently closed and it's not susceptible to agency or free choice, because those are things that have already happened and they can't be redone or altered. Well, according to the space-time theory, William, you have to think of the future in the exact same way. The future is just as closed as the past because it has a definite set nature, and all those events are out there lying in wait, I guess, for the consciousness that you have to experience them. Kobe, is this how people came up with the theory of infinite different dimensions? Well, that's not necessarily implied by the theory here, unless what you're thinking is that the possibilities where you do different things than what you actually do exist in different versions of quantum reality. There are some who hold such views. If you study quantum physics and you learn a little bit about the puzzling cases of the Schrodinger's cat, one interpretation of the physical experiments and theories is that there are branching vectors of quantum reality where other events happen and counterparts of you do those other things. But that's not the only possible interpretation. There's also the collapse theory, which says that quantum particles tunnel through infinite different trajectories before they collapse on one particular position. William, I guess that implies that our destinies are certain and everything is laid out. It would imply that, yes. One interesting thing that I think it's like almost a connection point here between ideas that people have in religion and ideas that people have in science, is that in some views of religion, sorry, I need to, Peachy over here is chasing something around the ground, it's distracting me. Let me take it away from her. Sorry, Peach. Okay, back to what I was saying. Yeah, according to this view, there's a set body of events that all exist. And it's just an illusion to think that there's some kind of unfolding of the events over time. Can you remind me what was my train of thought just before I had to go and deal with Peachy? Oh, the religious thing. Yeah, so with religion, people sometimes say that God is in control of everything, that God has a plan for us, and that whatever happens is totally under his direct control, and we're powerless to change the will of God, obviously. If God exists and he's omnipotent, then whatever he wills is exactly what's going to happen. Sometimes people wrestle with the contradiction between that and the idea of human free will. Of course, God, they say, judges us, and you would think that if he judges us, then it has to be because we have free agency, not that he simply creates us to do whatever we do and then he makes the judgment. But that's a puzzling problem for people that are philosophers of religion and such. On the scientific side, there's also the idea of predestination and fate. According to the space-time theory, this is exactly what you should expect to be true, because all the events of space-time exist, and so you can't do otherwise than the existing set of facts that you're bound to witness. If that's the case, then free will would be something like an illusion that we think we have as we do our actions, but we really don't have the ability to act counterfactually. Was Cider religious at all? I don't know. I don't necessarily think so. I mean, in the academy, religiosity is underrepresented in higher education. So the higher people go up the education attainment scale, the less religious by statistical probability people are going to be. Just knowing that, and knowing that he's an American analytic philosopher, I would say it's perhaps a 50-50, so I couldn't report on that, to be honest. But some philosophers are deeply religious and others are quite secular, although I think secularism is a little more overrepresented in the highly educated elite circles of the academy. Today, anyway. That's not always been the case historically. But anyway, I wanted to tell you then, if the space-time theory is correct, which Cider says is a better view of reality than the confusing Newtonian conception where we have to explain how time moves, how then can we reconceive objects in ourselves according to the space-time theory? Well, I'm going to try and help you understand what that understanding would be by showing you some of these diagrams that are called space-time diagrams. Some of these are shown in the book too. For example, you'll see one on page 460, figure 4. So here's kind of the diagram that you're going to look at. These are two axes. We've got the horizontal axis Y, the vertical spatial axis X, and then this axis that runs through the intersection of them. Let's label it with T for time. Now, this is what they call a space-time diagram. It's sometimes called a four-dimensional graph. Now, to have a true four-dimensional graph, I would have to have a three-dimensional like pop-out to show you, where you could see height, width, and depth, the three spatial dimensions, plus the fourth dimension, which is time. Since I'm working with a two-dimensional board surface, I can't possibly represent on the board the three spatial dimensions and the time dimension. So what you have to imagine is that this is our familiar horizontal spatial axis. This is the vertical spatial axis, and this is like running through the intersection of them as though it was like a three-dimensional image. Okay, now, on such a space-time diagram, we can draw and graph the existence of a given object in space-time. Like, for example, a person, like you. So I know that many of you guys are in your early years of college, so if it's 2021, that means some of you maybe were born in like 2002 or 2003. So let's suppose we have a person that was born in 2003. So I'll draw this little mark along the t-axis to designate 03. And suppose that this same person is going to live a long, happy, healthy life, like I hope you can, and they live until the next century, 2100. Okay, so they 97 years. Now here will be the little graph that shows their overall existence in time and space. Okay, and at 2100, I draw this like hard edge because that's the end of the person's existence when they die. So this is from birth to death, the person's whole existence, graphed out on the space-time diagram. Now I have a couple of little questions about features of the graph that maybe I want to see that you understand, okay? Why then do you think this is shown? Why do you think that I have drawn the stick figure character smaller in the x-axis here at 2003 than, let's say, further along in the middle of the sequence? Why do you believe that I show greater vertical height here at this point of the graph than over here? In other words, why does the stick figure look so small at the beginning of the sequence? What do you think that is trying to show in the graph? The variation in the vertical height. Okay, good, Kobe, because as a newborn, at the beginning of your timeline of existence, you're small. You're physically small, okay? And we all understand that. What's a baby born today going to be? 7-10 pounds or something like that, and then you're a full-grown adult now, 150 whatever pounds that you are now. So this growth along the x-axis just shows spatial growth in size of the object over time. Now another question about the graph. What do you think it means that we have this horizontal streak that extends along the t-axis? So height along the x-axis is like growth in vertical height. What does it represent, this extension along the t-axis? Why is it that there is that stretched out extension on the graph where the human shapes appear? What is that supposed to signify? What do you think? So we talked about the x-axis and the variation of height of the stick figure. Now I'm talking about the t-axis and the horizontal extension that it has where there's these stick figures on the line. What do you think that symbolizes or stands for? I'm sure you can judge. It's representative, you say, of their age, Naaman. Well, one way to say it is their age, but I would rather say it as it represents the, not physical growth, but the, Elizabeth, you're also saying the word age. Well, sort of, but the idea is that it's the extension of the object through time. It's how long the object exists or endures through time, okay? So like in this case, the human being lives for 97 years, so they occupy a good stretch along the t-axis, and the longer lived the object is, then the more points along the time dimension it would occupy. So imagine that an object existed for just an instantaneous moment, like a particle of antimatter erupts into the universe and is instantly annihilated. Then it would only have one vertical slice, and there would not be any extension along the t-axis. But for us anyway, thankfully, I guess, we have some extension in time that we are able to live. So we live for some number of years. There are other objects, obviously, in the universe that have much more duration than us. Think of planets, I don't know, stars, mountains, trees. Even some animals, I guess, can live much longer than us. But anyway, we have a certain span of time that we exist, and that's shown in the graph. Now, okay, according to the space-time theory that Cider is trying to really emphasize and encourage us to embrace, according to the space-time theory, objects take up they have both spatial and temporal parts. So it's a very important idea to understand the idea of temporal parts. This is a key aspect of space-time theory. So let me start with the spatial parts, and then I'll talk about temporal parts. Spatial parts of an object are just its different physical parts that occupy space. In the case of, let's say, like a chair, like you see I'm sitting in this chair here, one part of it is the chair's back, another part of it are the legs of the chair below, another part is the surface that you see, the seated surface that you would sit on of the chair. And so those are the different spatial parts of it that cause it to take up mass and volume in the universe. Now, for me and you, human beings, we have spatial parts as well, and obviously those are just the familiar body parts of your anatomy, so your hands, feet, legs, torso, and head. My body parts, the spatial parts of me, are the reason that I occupy some space as I sit in this chair, and that's also why I crowd out, or as they say, occlude other objects from occupying the same space, because I'm taking that space up. Okay, so we take up space in the world by having spatial parts. But the theory of space-time says that we also take up time, we endure through time, so we occupy space by having spatial parts, but we occupy time by having what are called temporal parts. Now, let me tell you exactly what a temporal part is. A temporal part is just an object at a single moment of time. An object at a single moment of time is a temporal part of that object. So suppose, here's a little terminology, some shop talk. Sometimes metaphysicians, people who spend a lot of time working with metaphysics as philosophers or even as scientists, they use the term for the object that's extended through space and time on a graph like this as a space-time worm. Worm just as a sort of generic phrase to express the idea that on the graph it appears to take a worm-like structure because it extends along the temporal axis and also occupies these other spatial dimensions. Now on the space-time worm, if you were to cut like a single cross-section through it, like if this is a loaf, then this is like one thin deli slice, just cut through it, that one individual instant of time in the career of the object would be one of its temporal parts. So a temporal part of an object like you or me is just that whole object, but just at one single moment. So let me try and really hit this home and make sure it's coming through to you. Let me ask this question. Suppose, so we all take photos and pictures, right? Say that there's a photo taken of a person, a still frame image. Question, how many temporal parts of the person are shown in that photo? So like, your yearbook photo or whatever, how many temporal parts of you are in that picture? Are displayed in that picture. So question, it's good, Naaman, there is one. So you're giving me the right answer. Let me, if I may, ask a follow-up question. So to those saying one, which is correct, why is it that in a photograph, there's only one temporal part of the person? Basically, I think you would understand it because you gave me the right answer, but let me hear it from you. Why do you say that it's just one temporal part in that picture? Correct, but why? Always be ready with the why question. So why is it just one? It's a single moment in time, exactly. A photo captures just one instant in a person's existence, so the light that's captured by the photographic device can be viewed, but it's just showing one image. It's not got any duration. So it's just one moment, and that's one temporal part. Now here's another question. Suppose it's not a still frame photo, but a short video clip, like a little TikTok video or something. Even if it was short, like 15 seconds, how many temporal parts of the person do you think are shown in the short video? Now, this is kind of a trick question. I'm going to be fair and tell you that because I know you can't give me a specific number. But what kind of answer do you think would be the proper type of answer in response to that question? How many temporal parts of a person are shown in a short video clip of them? Good, Ivan, yes, correct about the photo. But I'm now switching the example to video. Let's say it was a 15-second video. How many temporal parts of the person do you think would be in that little video? Well, there would be multiple. Justin, you're going all the way with infinite. Kobe, you say more than one. And you say it depends how you break down time, William. That's also good. So, Sergio, you say if we use seconds as the units for the amount of temporal parts, then in that case, I guess it would be 15. But obviously, there are many more than just seconds in terms of how you can subdivide time down to the least unit. Okay, so what the right answer sort of is this. And Angel, you say, doesn't it depend how much they're moving? No, it doesn't, because even if you're standing perfectly still, you're taking up moments of time throughout the entire extent of that. So it doesn't have anything to do with whether the person's moving, actually. So it's this. There are just as many temporal parts of the person shown in the video as there are what in the video? As there are moments of time. Moments of time. Now, what is a moment of time? It's the least possible unit of time. So it's not just seconds, not just half seconds or tenths of seconds or milliseconds even, but the minimum unit of time that could possibly be before you can't divide it down any further. So yeah, Ivan, it can't just be individual seconds because we know that there's many things that can happen even in 1 second. You ever watch sports and you see like a person get off a shot in like 0.3 seconds? So you know that many events can happen within even 1 second of time. So what's the least amount of time that there could be? Well, sometimes people say how many frames are on the camera, but even that's not exactly the right answer because as you know, how many frames there are has to do with the technological limitations of the device. Some devices can show 30 frames per second. Some can record at 60 frames per second. And then there are some super cameras that can do like 1,000,000 frames per second. So you got to think about this as like God's camera, not just how fast a technological item could process images, but how many images could ever be processed because that's the maximum number that there actually are. And so Sergio, you actually have, I think, a very good response there, which I was just about to say. In physics, there's a man named Max Planck, famous physicist, and he discovered what is referred to as the Planck length. The Planck length is considered to be the least unit of physical space, such that you cannot further subdivide space into units that are smaller than it. And so since space and time are connected according to the space-time theory, we should expect that there would be a minimal Planck time as well. So an infinitesimal small unit of time that can't be broken down more than that. Anyway, guys, there would be a huge number of these temporal parts, even in a short viewing sequence. So I want to stay with the temporal part stuff for just 1 or 2 more moments here and ask a couple of last follow-up questions. According to the space-time theory and what you're learning about these temporal parts, what do you think is the answer to this question? Are you fully present right now as you attend this lecture? Are you fully present? Are you here? Is the whole person that you are here at this lecture? Yes or no? What's watching this lecture? You, the whole thing that you are, or no? Yes or no? Are you fully present right now watching this? According to space-time theory. According to space-time theory. Kobe, you say yes. The answer is no. So let's try again. Why is the answer no? Think it through. Why is it that according to the space-time theory, no, you're not fully present? I mean, some of you's present watching this, but not the whole thing. Why do you think that's the answer? Yeah, so according to the space-time theory, no. Why would you say? I love it when the student gives the explanation and then I can, kind of work through it. No, because you exist in the future and past also. That's right, Naaman. So the right thing to say is this. Some of you's watching this lecture, sure. But what part of you? A couple of your temporal parts. So the temporal parts that exist in a little cross-section of your timeline that occupy the timeline between 10 a.m. and 11:15 a.m. on this particular date. But there's all kinds of temporal parts of you from like K through 12 that I never had anything to do with, that I never met. And then there's all kinds of temporal parts of you that are lying out ahead in the future. You graduating this college, getting married, maybe having kids, starting a family, starting a business, later on getting retired, watching your kids grow up, taking them to their wedding. All that future stuff is not attending this lecture. But on the space-time theory, all of it's real. The future stuff's real just as much as this, just as much as the past. So the answer is that you're not fully present as you sit here, but some of your temporal parts are. Is it the same temporal part sitting there now as the one that started at the beginning of the lecture? No. A different member of the sequence of your temporal stages is watching this point in time, as compared against the earlier temporal part that was watching the beginning of the lecture. So you're a series of like stages, as though a stretched out accordion structure. And at each individual instant of time, there's a unique and different temporal part of the space-time object. So yes, that's all correct. Kobe, you say, oh, okay, so me as a whole is not watching the whole lecture. It's just a finite amount of temporal parts. Correct. So what is the whole thing that you are on this conception of space-time? The whole thing that you are is the aggregate set of all your spatial and temporal parts as though collected into one big structure. But you never experience the whole thing at a given time because your consciousness only perceives one of the temporal parts at a given moment. Although I guess you do have memories, so your memories remind you of the temporal parts that you had been before, that were part of you as the past existed. Okay, so a temporal part of an object is the same spatial size as the object. So like this temporal part of you, if we were to like freeze frame reality, it's your whole body spatially, but it's not the same size temporally because you're stretched out in the space-time theory, not just in space by having spatial parts, but you're also stretched out through time by having these temporal parts located throughout the duration of your existence. So you're the sum total of all the temporal parts. Now let me read it from the book a little bit, and you can kind of connect it to what he has said. He says this, I'm trying to find the key quotes. In addition to the dinosaur and the person, some other temporal parts are represented in the diagram. A temporal part of an object at a time is a temporal cross-section of that object. It is the object at that time. Consider the temporal part of a person in the year 2000. The object is the same spatial size as the person in 2000, but the temporal part is not the same temporal size as the person. The temporal part exists only in 2000, whereas the person exists at later times as well. The person herself is the sum total of all of her temporal parts. In contrast to the ordinary conception of moving or flowing time, Christian, I thought it was a good comment, but anyway, in contrast to the ordinary conception of moving or flowing time, the space-time theory says that reality consists of a single unified space-time which contains all of the past, present, and future. Time is just one of the dimensions of space-time alongside the other three spatial dimensions. Just as it appears to be in the diagram. It doesn't flow, it just sits there like space, containing everything. Okay, so next he says, to further deepen our comprehension of how we are supposed to reconceive of space and time along the lines of this theory, we have to now be brought to awareness of how, according to the theory, space and time are more similar than we usually think. So time, you're being asked to consider it to be more similar to space than you had thought before learning about the theory. So let me try and point out what he means. He says there are three major similarities between time and space, according to the space-time theory. Okay, so one is what he calls in terms of reality. The second similarity is in terms of parts. And then the third one he mentions is in terms of these two words here and now, in terms of the words here and now. Okay. So I'm going to start off with the first one. How is it that space and time are similar in terms of reality? Okay, here's what he means. According to the space-time theory, space and time are similar in this way because consider this. An object in space, hey Eddie, an object in space, whether it's close up to you or far away, it's just as real in either case. So see this marker that's standing in front of me or that I'm holding in front of me? It's obviously a real thing. It's no hologram. This is a real deal marker. I'm writing with it so you can tell. So it's real. Question, would it still be real if it was farther away from me? Instead of being right here in front of my face, what if I put it way over there? Isn't it still real even though it's a little further away at the outstretched arm's distance? Yes. What if I leave the marker here and I get up out of this apartment and I go on a run 5 miles away and I leave it behind? Now we're 5 miles apart from each other, but isn't it still real? Of course it is. It's not that it stops being real when it's a certain remove away from me in space. And that's generally true no matter how far it goes. So if I took the same marker here and I put it on a space shuttle and send it over to the moon, and then someone drops it on the moon and I'm still on the Earth, it's still real. So it's just as real when it's in my face as it is when it's a million billion light years away or any intermediate distance in between. So the point to take away is simply this. Objects that are close up in space are just as real as objects that are far away in space. And the same is true of time, according to the space-time theory. So consider how far away events are in time. Sometimes when we talk about time, we say, here's the present moment, this is now, and then way out ahead of me is some future thing. Like you're thinking about your retirement, and you're like, oh, that's way out ahead of me in my life. That's so far ahead. And maybe you look back, and you're like, oh, look at these baby photos of me. Man, back in the day, that's so far back in the past. The ordinary way people think about space and time, or at least time, is that the past is not real anymore. It's gone. It's over. And the future is completely open, and it's undetermined. And so people think that if it's not the present moment, it doesn't exist. But the space-time theory says that's not true. Events that are far ahead in the future are just as real as what you're experiencing right now. So you sitting here in this lecture is not the only real moment. Moments that are 5 minutes ahead, 10 minutes ahead, an hour ahead, a year, 10 years ahead, a million years ahead, all of those events are just as real as the present moment. So space away from you, distance in terms of space doesn't change how real things are, and neither does distance in time, according to the theory. So, I mean, Eddie's sitting here. I'm going to try and write the definition of the concept. Maybe I'll write it above so that I don't have to make him leave. Because it's a nice treat. He never comes up here, so this is kind of a special thing. Anyway, in terms of reality, what this means is the following. Objects that are far away in space are just as real as objects that are close. And the same is true of time. The same is true of events in time. So an object doesn't have to be physically present to me in space for it to be real. If it's present, like this is present to me, it's real, but it's also real even when it's far away at a remove spatially. And the same is true of time. So the present moment is clearly real. I'm sure you agree that this thing is real that we're doing right now. But on the space-time theory, that's not the only thing that's real. The things that are happening that are far away in time, not just in space, are just as real as this now. Okay. And don't misunderstand it. It's deeper than just saying, oh, they will happen. Like they do exist. Like the physical body of you as like an older man or woman exists in this universe currently. It's just that the temporal part of you that's watching this lecture doesn't have access to it. But that's the case, I guess, according to the theory. So one similarity in terms of reality. When you think about how these things are somewhat similar, you start to come to a deeper and more full understanding of the nature of this theory. Okay, so the second one is in terms of parts. Now what that says is just this, that objects occupy space by having spatial parts, and objects occupy time by having temporal parts. So here we go. I'm just going to type it into the chat. Okay, so that would be my note for the second similarity. Objects take up space by having parts that are spatial parts, like Eddie here. You know, he's got his big belly and his head and his legs and his tail, and he occupies space on this table by having those body parts. But he also occupies time, just as any of us do, by having temporal parts. So I remember the little temporal parts of Eddie when he was a small kitten, just a couple of pounds, 3 or 4. Now he's 13 pounds, and he seems to be getting bigger every day. So anyway, though, he's extended throughout time by having these temporal parts. I hope he has a lot of them. So he has a nice, full, long life. But he occupies space by having the spatial parts. So his mass and volume and shape that takes up the space of the table is the body parts, the spatial parts. But the length of time that he's going to exist is due to the existence of all the temporal parts collected together in an aggregate. Okay, and then the third one is in terms of the words here and now. So I'm going to put the note about that in the chat as well. Okay, sorry, here we go. Okay, so what it says is third similarity in terms of the words here and now. And that means both are relative terms whose meaning depends on the context of the speaker. Okay, so I have a question. It's kind of a trick question, so think about it first, but give the answer when you can. Where is here? Where is the place located that we call here? Where is here at? What location does here refer to? Does it refer to one objective location? Is there a point on the map which we all point to and say that's where here is? Not necessarily, but tell me. It depends on the person, right? Well, it depends on where the person is when they say it, you know? So for example, if I say, speaking right now, here we have Governor Gavin Newsom. So Gavin Newsom's the governor here. Suppose that I talk to a friend on the phone in New York and they say, oh, well, here the governor is Andrew Cuomo. Are we contradicting each other? Because I say the governor of here is Newsom, and he says the governor of here is Cuomo. We're not contradicting each other because the word here doesn't refer to the same location when we both use it. When I say here, I'm saying it from the West Coast in California. So my word refers to the spatial environment around me when I say it. And the other speaker on the East Coast, when they say the same word, they're referring to the local environment around where they are at. So if I tell you right here, Eddie's hanging out with me, and you say, Eddie's not hanging out with me here, well, we're not contradicting each other, because when I say here, I'm referring to my apartment. And when you say here, you're referring to wherever you're watching this at remotely. You know, this lesson, this part was a little easier to do face-to-face, I gotta be honest, because at least then we would all be in the same room, and I could be like, okay, guys, so here is Cal State Fullerton, right? But people that are taking this class in another university are referring to a different school when they say here. But anyway, that's clear enough, right? That the word here doesn't have a universal objective position. It depends on the space where the speaker speaks the word. And same is true of the word now. Okay, so here is like a relative spatial word, but now is a relative temporal word. So now I have this question: when is now? What time of day or what time is now? When is now? When is the time now? What time does the word now refer to? What do you think? It's similar to your answer for the previous, but so now is always passing, true. What time does it depend on though? So if I say, open your books right now, or get on the computer right now, what time would that refer to? It would refer to whatever time it was. Well, when you say it depends on who's saying it, it depends rather on when they are saying it, not so much who's saying it, because two different people at the same point in time would have referred to the same moment if they both said now. You understand? So that wouldn't depend on who it is, but rather when it is, okay? So when the person says now, that's now relative to that speech act. So when I tell you guys, right now we're learning about Einstein, what is that time point that I'm referring to? I'm referring to April 15th, 2021, 11:07 a.m. But if 100 years ago people were studying Einstein when he was still alive, 1921, they're sitting in their university classes and they're like, let us learn about this up-and-coming revolutionary physicist who has changed our thinking about space and time. Right now, let's study that. They would not have been referring to 2021. They would have been referring to the time of 1921 and the local time they were saying that. And if there are speakers in 100 years from now, 2121, and they're like, let's now study the beginnings of the 21st century. What a turbulent time it was with the coronavirus and people trying to have a coup to overthrow the US government. anyway, now we're going to study that history of the recent past. Well, they would not be referring to the time that we are at, but rather the time that they're speaking in the future. So this disabuses us of a common notion. When you think of the word now, ordinary folk usually just think there's only one moment now, and it's right now, and no other moment in time could ever be the present moment. But on the space-time theory, every moment, relatively speaking, is now if there's a temporal part of a speaker that says the word now at that time in space-time. So there's no unique moment now. Now is relative. It depends on the context of the speaker, just like the word here depends on the location of the speaker. So that's it. That's the three similarities between space and time. At the end, he says, this gives us a much better and actually more empirically supported view about how to consider space and time. And it does eliminate all the perplexities of trying to account for how it moves. Now we don't say it moves. We just say it's all there, and it contains every event of the past, present, and future. So nothing's starting, nothing's stopping. It's all just out there. But, you know, some people, he says, find the idea of space-time to be so counterintuitive that they cannot accept it. And I know it's not really so much scientists that have this problem, but everyday people and some philosophers kind of, they resist the idea of space-time theory because it's so weird to our common sense. And he imagines a person having that reaction. So he says, somebody might say this: no, past and future objects do not exist. The past is gone. The future is yet to be. Things do not have temporal parts. At any time, the whole object is there, not just a temporal part of it. There are no past or future parts left out. Now is not like here. The present moment is special. It's not like when someone says here and they just refer to the random area around them. So these are the sort of common sense pushback to the idea. One other possible critique or intuitive resistance to the idea is that according to the space-time theory, nothing really ever changes. And some people say that's just too counterintuitive to be true. Let me think about this with you and see if you can understand the point. Why would it be perhaps true to say that technically speaking on the space-time theory, nothing changes? Let me give you this example and we'll play around with it. Suppose that someone gets a haircut, right? So they had long hair before the haircut, and then they get a real different look, so they cut their hair real short. Now you might look at the person before and after and say, oh yeah, you've changed, your look has changed. You know, your haircut has changed, your appearance, you had long hair, now you have short hair. Can anybody think about why on the space-time theory, there hasn't actually been anything that has changed? Why would you say that that's the right way of looking at that example? Because to all appearances, the person looks different. So how come on the theory's basis, we would say there actually has not been anything that has changed at all? How come that doesn't count as change, at least on the theory's lights? I'll draw another space-time diagram while you're thinking of your answer, because that'll help. Y, X, T. So you say it's because they still have hair? No, that's not it, Kobe. Got to go deeper. Think deeper. There's been no change because why? Say that this is the time slice where the person was going to the salon, and then here just a few moments later in the day after the haircut, this is the time slice afterwards that has the shorter haircut. How come you would say that although there appears to be a difference here, nothing has changed in fact? Because why not? The diagram, I'm hoping, will help make this more clear to you, or something will click. When you look at the diagram, I'm showing you two vertical slices which will display the two different temporal parts. The one part where there was longer hair and the subsequent part afterwards in the same sequence where the hair is shorter. Even though the two parts have these different hairstyles, nothing has changed because the two parts themselves, what? I would love it if someone could say this because it helps me to understand that it's making sense to you. Maybe it doesn't. Maybe you're just sitting there like, this is bizarre. I can't think of any of this stuff. It's way over my head. So help me make sure that that's not true. Why is it that there's been no change? There was a haircut, but nothing changed at all. Because if you look at the whole diagram, what do you think I'm trying to indicate here? Got to try a different answer, Kobe. Sergio, everything already exists, so ultimately nothing technically changes. Perfect, Sergio. You got it. Kobe, read that comment, think about it, and look at the graph. So the whole space-time object has existed forever. All of these stages are eternally real. You got to get out of the thought that the present moment is the only real moment. The future moments are real, the past moments are real. So this part of the temporal object, the stage that has the shorter hair, has always been at that position in the timeline, and the other temporal part with the longer hair has always been on that position in the timeline, but the overall sequence of all stages hasn't changed at all. That one part with the short hair has always had the short hair. That one part with the long hair has always had the long hair, and the individual temporal parts are not changing. So instead of talking about, Kobe, what's your second comment? It's only a small section of temporal parts. No, that's not what I was trying to do. I was trying to indicate to you that the two different parts which are marked along the sequence have always been in their respective positions in the sequence. It's not like the second one pops into reality when the person gets the haircut. You understand? That temporal part is just there, and none of this stuff is moving or changing at all. So the sequence of events is not movement. It's just an order. Okay? Now, what we should say then, in order to have a correct analysis of what we call change, is not that the same thing has changed, but rather that there are two different whats that have different qualities. So change now gets redescribed as having two different blank that have different features. So what is the different way of talking about change according to this theory? We say that it's not actual change, but in a way it looks like it because there are two blank that have these different qualities. What's the thing I'm trying to blank out in that description? Instead of calling it change, we say that when things appear to change, there are two different temporal parts that exhibit different features, correct? So like right now, I'm wearing this shirt, and yesterday I was not wearing that shirt. But I haven't changed, or even my appearance hasn't changed, because the temporal part of me from yesterday is still there with that different outfit, and the temporal part of me today exhibiting this outfit is just a different part of the overall sequence of stages. But none of these things has started or stopped happening because the past part's still there. This part will always be here. So two different temporal parts having different qualitative features. For Ted Cider, he says to anybody who resists the space-time theory because it eliminates the idea of change, he doesn't see that as a fatal objection because he says we simply have to reorient the way we think about change. We can recapture the concept of change in space-time theory by saying that it's whenever two different temporal parts of a given object exhibit different features. So if I shave today and I come in clean-shaven next week, you might say, yeah, he's got a different look now. But in fact, according to the space-time theory, the post-shaved clean version of me is just one of the stages that's on the other side of this divider. And there hasn't been any change because all the stages have always been there, including the ones leading all the way up to my death, back to my birth. They're all just there. So it's weird stuff. I guess if it's true, then you have to wonder, why is it that we only experience one moment at a time? I think it would have to be because we would be overwhelmed by the multiplicity of contradictory events and perceptions. There was this one YouTube video I watched a while back, and it made me think about that a little bit. I don't know. It's kind of an indirect connection for sure. But you know how sometimes people spend their time making the weirdest YouTube videos? Like someone made a video where it was every episode of Friends superimposed on every other episode. So while you're watching it, it's like insane. You're seeing like hundreds of episodes, and they're all kind of, the audio and video is confusing. So it's like all these scenes together. Now, if our mind was thinking about all of the temporal events in our existence at once, it would be kind of like that. It would be just like a mess. So I would argue that if this is actually like physically true in the universe, if this scientific theory is correct and we are stretched out throughout time and space, then perhaps the reason that our consciousness doesn't allow us to observe all the events at once is because it would be overwhelming and chaotic, and therefore it creates a linear ordering so that we kind of have a streamlined experience. But anyway, guys, food for thought, I guess. I'm going to let you go, though, and if you look at our syllabus, we're pretty well on schedule. One thing I didn't get to talk to you guys about today was David Lewis's article called The Paradoxes of Time Travel. I'd like to maybe mention just a couple things about it at the beginning on Monday, or sorry, I meant to say Tuesday. I know we're Tuesday, Thursday. So try to read the Lewis and do read the Descartes 6 meditation. And I'll be distributing the essay prompts for the second essay over the weekend, and we'll talk about it when we come back on Tuesday. So that's just the next few things to look forward to. But other than that, guys, let me know if everything's fine. And once you say goodbye, I'll sign off and close the stream for today. So everything's fine and good? Okay, thanks, Kenny, Sebastian, and everyone else. Appreciate it, and be in touch if you need anything. I'll be checking email each day. Okay, see you soon. Bye-bye. I guess if the space-time theory is correct, then maybe destiny will bring us together again on Tuesday, like it already has, I suppose, and then nothing we can do about it. All right, guys, have a great one. Take it easy.